We are given a negative feedback system with the plant transfer function Gp of s equals 2.2 divided by 1 plus 0.1s times 1 plus 0.4s times 1 plus 1.2s, and the compensator Gc of s equals k times 1 plus T1s divided by 1 plus T2s. The external disturbance input is D of s. It is desired that when the disturbance is a unit step, the steady state error should not exceed 0.1 unit. We are asked to find the minimum value of k. To know more about the concepts used to solve this problem, kindly refer the NPTEL Control Engineering course, Week 3, Lecture 4 by Professor Ramkrishna Pasumarthy of IIT Madras. We can use the following concepts to solve the problem. The steady state error is the difference between the reference input and the output of the system as time goes to infinity. For LTI systems with multiple inputs, the output to each input can be determined individually, and the superposition principle can be used to obtain the overall output of the system. So, we are given the plant EP, then a disturbance input T of S, compensator G, the reference R of S, and a negative unity T of S is the output. So the transfer functions given are dp of s equals 2.2 divided by 1 plus 0.1s times 1 plus 0.4s times 1 plus 1.2s, and t of s, the compensator is given as k times 1 plus t1 plus t2s. We are asked to find the minimum value of k for which the steady state error when the disturbance input is unit step is less than or equal to 0.1. So let us look at what the output of the system is to the disturbance input. For that, we have to find the transfer function T of s divided by D of s. So we'll set R of s to 0 so that we can find the output with respect to only the disturbance input. So let me redraw the block diagram again, setting R of s to 0 just so that things are much more clearer. So you'll have GP here and the output, then the summing point with the disturbance input, and then you have the compensator block. So the negative sign over here will get propagated to this summing point or the block or the compensator block since R of s is 0. So you can put the negative over here. So this is a negative feedback system with the forward path gain of Gp and the feedback path gain of Gc. So the transfer function will be T of s divided by E of s equals Gp divided by 1 plus B Gc. So you can substitute Gp and Gc here. So you'll get something like 2.2 times 1 plus T2s divided by 1 plus 0.1s times 1 plus 0.4s times 1 plus 1.2s times 1 plus T2s plus 2.2k times 1 plus T1s. So now we can find the output when the disturbance is unit step. So T of s will be equal to, let me call this transfer function E Td of S times D of S. So using the final value theorem, you can calculate limit t tends to infinity, t of t is equal to limit s tends to 0, s times t of s. So that will be equal to, I can substitute c of s from the above equation. So you will get limit s tends to 0, s times t of s is t c d of s times d of s. So d of s is a unit step input. So that will be equal to limit s tending to 0, s times ECD of s times 1 by s. So you can cancel these s's. So this will get cancelled, and then this will be equal to limit s tending to 0 ECD of s. So the final value of the output is limit s tending to 0 ECD of s. So let us substitute s in the transfer function. So when s tends to 0, this term will go to 0. So all these terms that has s in them will go to 0. So finally you will get 2.2 divided by 1 plus 2.2k. So you'll get this is equal to 2.2 divided by 1 plus 2.2k. Now since r of s is 0, the output limit s tending to 0 s e of s for the disturbance input 1 by s should be less than or equal to 0.1, since the steady state error is being measured with respect to the 0 reference input. So we can substitute for this. We will get 2.2 divided by 1 plus 2.2k is less than or equal to 0.1. So we will get k is greater than or equal to 9.54. So from this, the minimum value of k, I'll call it k min, is equal to 9.54. So that is the answer to this problem. So the minimum value of k is 9.54. Thank you.